Okay, then let us officially kick off this meeting. Today, Jordan will talk about the dressing field method. We are all super excited to hear about this. So without further ado, Jordan, the floor is yours. Take it away.
Yeah, thank you, Philippe. Well, I hope, since I know that many of you already have heard me talk about this, perhaps even saw some of the slides I will present. Well, I will try to make it entertaining still, or at least since it is more also the discussion session, you can interrupt me, of course, and we can discuss in the middle of anything, so no problem, don't hesitate. So the point is to indeed present, following the seminar by Axel, to present the dressing field approach, which is complementary, and we join the FMS approach, as we will see, as a way, the tool, the dressing field method is a tool to try to reduce gauge symmetry and to perhaps reach for a gauge invariant formulation of a gauge field theory, basically. So the plan is as follow. I give a tiny bit of contextualization about gauge to discuss gauge symmetry and to motivate the use of the dressing field method in that context. I will remind, again, sorry for those who already know a lot about this, but give the example of the rhetoric model, and because it is a place where I would say the dressing field approach maybe shine particularly. And even though it is not the only one, there are of course applications to gravity, to conformal geometry, and I will give, in the final part of the talk, give a preview of extensions to the dressing field method, especially to diffeomorphisms, and discuss the open question. So let's start from this. So the gauge field theory framework is central to fundamental physics, as many of you already know. It is driven by the gauge principle, which is a powerful heuristic to constrain the space of acceptable theories. And indeed, both general relativity and the standard model are gauge theories. So there seems to be something to that gauge stuff that we need to understand better. We have a problem of interpretation, though, which, at least in the physics literature, when you scan the physics literature, it is not often clear. The message is not uniform as to what are gauge symmetries, what do they mean exactly, of what they are symmetries, basically, because we know they are at least formal symmetries of the Lagrangian, of algebraic expressions. But the geometric viewpoint is that the gauge group, so the mathematical incarnation of gauge symmetries, belongs to the group of automorphism of a fiber bundle, right? So I suppose most of you already know what is a fiber bundle. Basically, it is a structure that if M is your spacetime, okay, quote unquote spacetime, a fiber model is something that will enrich the structure of spacetime by giving an internal structure to each point of the spacetime, right? Over each point of spacetime, there is a fiber, the fiber structure, and this is where the richness of gauge field theory comes from. And so those automorphisms project into the diffeomorphism of the spacetime manifold, of the base manifold M. So the gauge principle, from the geometric point of view, is an abstract generalization of the general relativity principle, or general covariance principle. So in a way, you would expect that the kind of understanding that you can get about the general covariance principle should shed some light onto the gauge principle and the meaning of gauge symmetries. At least this is my contention. I recently gave a short seminar about this. Maybe I can repeat it here at some point to discuss. One subtlety that appears is, for those who already know a lot about the early history of general relativity, is the Kretschmann objection against the general covariance principle as key to GR physics. The objection was that any theory could be, with enough cleverness, could be rewritten so as to be generally covariant, especially using the Levi-Civita tensorial calculus. So what give? And the objection pushed, at least the discussion around the objection, pushed to recognize maybe the distinction between artificial and substantive general covariance. So artificial covariance would presumably encode no physical features. It would be purely a redundancy of the formalism indeed, whereas substantive general covariance would have a physical signature. And presumably, of course, GR would display such a substantive general covariance. Mutatis mutandis, there is the exact analog. A generalized questionable objection can be leveraged against the gauge principle, which basically would say, well, given any field theory, I can always rewrite it, being clever enough, so as to display the gauge symmetry, or local symmetry. And so again, it seems there need to be a distinction between substantive and artificial gauge symmetries, where again, the artificial kind would encode no relevant physical features. So the question is therefore the one of the demarcation criterion between the two. And the one good, robust criterion seems to be the trade-off between gauge invariance and locality, as many of you know. Even if you suspend judgment about the importance of locality in your theory, if technically you don't care that much about using or not a theory which displays non-locality, at least you can recognize that there seems to be a situation where for some gauge symmetries, when you try to eliminate them, you end up with a theory which is non-local. And so such gauge symmetries, you would call them substantive, because, and these in contrast to the artificial kind, which can be eliminated without losing the locality of the theory, right? So there seems to be at least these two classes of symmetry. And I guess when you want to interpret a theory, it is a feature that is interesting to notice, that if you try to do away with the symmetry, then you end up with non-locality in your basic field variables, which seems to indicate, since gauge invariance presumably is where degrees of freedom, physical degrees of freedom are hidden, right, located, it would mean that the fundamental degrees of freedom in a substantive gauge theory are non-local. So there is a non-locality that comes from gauge physics, even at the classical level, which is non-quantum. And so here is the motivation of the dressing field method, because it is the question of implementation. So admitting that the criterion is a first good one, the question is, presented with any given theory, how do you detect if the gauge theory of that theory is or isn't artificial? And I would argue that the dressing field approach, which I'm going to present to you now, would allow an easy, almost algorithmic way to adjudicate that question. So what is the dressing field method? So let me first try to give, just to fix notation, to present you what would be the basic setup for a gauge field theory. So you have a gauge potential, which is one form on your spacetime manifold, with value in the Lie algebra of a H, which is in this case the global symmetry group, and its field strength is a two form with value in the same Lie algebra. Matter fields usually they are section of associated bundle. To a practical purpose for now, you can just think of them as simply function from the base manifold to a representation space for the group, for the symmetry group. And of course, you have the covariant derivative, which implement the minimal coupling between the matter field and the gauge potential. Now you have also the gauge group. So the gauge group is a set of maps from the base manifold to the structure group. And I insist on the fact that there is an action of the gauge group on its own elements, right? So if you take one element, say alpha in this case, you see it as a field, right? As a map from space-time to the group. Then another element, gamma, will act on it, gauge transform it, so to speak, in a way which is non-arbitrary, but given by this conjugation action. And it will be important for the next for the discussion of the whole method, actually. So the gauge group acts on the variables in a way that you are familiar with, I suppose. So it is non-homogeneous on the connection, and it is homogeneous, gauge tensorial, so to speak, on both the field strength, the matter field, and their covariant derivative, hence the name of covariant derivative. And so this is the kinematics, basically. And the dynamics is given by the selection of Lagrangian functional, right, which is supposed to be, or required to be, gauge invariant under the action of the gauge group, meaning we have this equation that must hold possibly up to boundary terms and exact terms if you are interested rather in the invariance of the action rather than the Lagrangian. Fine, so that would be the basic setup, right? The kinematics here and the dynamics given by the Lagrangian. So now, what is the basic proposition of the dressing field approach? it is the following. So suppose that you have a subgroup of your structure group, of your global symmetry group, to which correspond obviously a gauge subgroup, K, calligraphic. And now imagine you have a map from the base manifold to that subgroup K, which will be defined by the way it transforms under the K subgroup, gauge subgroup, right? It should transform on the left, as shown here, right? Basically, like a matter field would, right? It's a gauge tensorial transforming on the left by the left representation of the gauge group. So once you have obtained or located, built such an object, you can construct the dressed or composite fields, which are like this. So of course they very much resemble the gauge transformation that you have here. So the connection dressed inhomogeneously, so to speak, and all the other objects dressed tensorially in a way. And the claim is that those objects you can show are invariant under the subgroup K, right? We would call such a dressing map a dressing field. Right? So a U, so such a map with value in some subgroup transforming by definition on the left like this, you would call that a dressing field, and you could use it, you can use it to build invariant composite fields like this. I insist on the fact immediately that the composite fields are not gauge transformed field, right? The reason being simply that the dressing field U obviously is not an element of the gauge group, right? It is an element, you just have to look at the way gauge it transforms. The defining gauge transformation of the dressing field is not the one of a gauge group element, right? And so the consequence of that is that, for example, the dressed object that you have here are not in the gauge orbit of the original field that they are the dressing of. So I will come back to that later. Now, if you have built invariant under the subgroup K, presumably there might be some residual symmetry under what remains of the gauge group H. And so since you know already what is the gauge transformation of the basic field variable, so the A, phi, F, under the full gauge group H, the only thing you need to know to work out the residual gauge transformation of the composite field is the transformation of the dressing field itself. So by definition, it transforms under the K subgroup like this, but the question is open as to how it transforms under what remains of the gauge symmetry. So we have a particularly nice situation in which when the residual, what remains of the gauge symmetry forms a group. So for that, the technical requirement for that is that the K subgroup should be a normal subgroup, right? So that the quotient group is itself a group, to which corresponds a gauge group, which we call J. And now suppose that the dressing field that you have identified or built transform under J by conjugation like this, then it is very easy to show that the dressed invariant fields that you have built transform like normal gauge fields under the G gauge group, under the residual symmetry. So you can use those dressed objects, K invariant, as normal J gauge fields. And so this next proposition that follows from that is that since the K dressing field takes value in a subgroup of the structure group, of the global symmetry group, the formal invariance of the Lagrangian guarantees that you can rewrite the Lagrangians in terms of the dressed variable, the invariant fields that you've built. And therefore, by proposition 2, it follows that the rewritten or dressed Lagrangian is actually a J gauge theory, right? So you've started from a H theory and you end up to a J gauge theory. So you have eliminated part of the gauge symmetry. So that's why the dressing field is a systematic tool, an algorithm to build gauge invariants, to reduce gauge symmetries in gauge field theory. Again, I insist on the fact that the dressed Lagrangian is not a gauge fixed Lagrangian for the reason that I've stressed before, because U is not a gauge element, and therefore the dressed field are not element in the gauge orbits of the field that they are addressing of. So this is the technical.
Would you say it's partly gauge fixed? If that makes sense, such an expression?
I would no, I would not again, because again, precisely because the dress variable that you have here, they are not an element in the gauge orbit. You know, depending on what you mean exactly by gauge fixing. But for me, mathematically, a gauge fixing is selecting a representative in the gauge orbit of the fields, right? And it just, and for example, that object, so the A, the gauge potential, mathematically is a connection, right? It turns out that the dressing of a connection is no more a connection of the initial theory, of the initial underlying principal bundle. So
yeah, I meant it just naively in the sense like gauge fixing is in a way like imposing constraints, and you could impose constraints in the sense that you take away some degrees of freedom but leave others.
yes,
So it could be like that, or you could say, no, that's absolutely no consistent. I cannot say, I cannot partially gauge fix. That was my question.
Right. Well, I would say, again, it's a matter of exactly how you define things. Going by your definition of the gauge fixing, which would say, okay, let's impose a functional constraint and work with the results. In a sense, in that case, yes, you would say that, for example, the Coulomb gauge, for example, when you impose a constraint, solve, so you gauge, yes, you impose a constraint on a gauge transform, quote unquote gauge transform object, solve for the gauge parameters in terms of the field of the potential, for example, and what you end up with often is a dressing field in the mathematical sense. So indeed, but precisely, but in a sense that this is something I'm trying to raise awareness about, is the fact that many times things that are called gauge fixing in the physics literature are not gauge fixing at all, because you are performing an operation that moves you out of the mathematical space from which you started, right? A gauge fixing is selecting a subspace of a mathematical space, usually, mathematically speaking. And so when you dress, is moving out of the mathematical space.
So can I propose some, the way that I think about this is that A of U is this function that exists in the whole outside of the section as well, and everywhere, let's say on the orbit, but you can think of it as a projection. So the projection takes, so you can think of it, I think, in two ways, either as the pre-image of some projection or after the projection onto a given section.
Yeah.
And if I think it works in both ways. And after the projection, it is like a gauge fixing, or at least several examples would be like a gauge fixing, in that A of U would obey some equation like the Coulomb gauge fixing equation, or in most examples. But there might be examples which I don't know, where you get addressing that for which you can't really write as this kind of projection onto a gauge fixing section. I think that would be interesting to ascertain.
Yeah. Maybe a clarifying. Thanks you, Enrique, for the comment. Indeed, probably it would be easier for me to argue the case if I were to present the full mathematical formulation as I understand it now of the dressing field as living on the fiber bundle of field space and having a section, gauge fixing being a section in that space, and
Right.
Whereas the dressing field as the realization of the projection of that fiber bundle, which makes the distinction more sensible, more clear.
Right.
But maybe one example I could give that shows, and I don't elaborate on it here, but when you think, for example, of the case of the tetrad formulation of general relativity, you have a theory which is a local Lorentz symmetry. So Lorentz is the gauge group in that case, and A is the spin connection. One object that satisfies the definition of a dressing field in that case is the tetrad field. And the dressing of A via in that case would be simply, well, the construction of the Christoffel symbols, right? So you dress, so to speak, the spin connection with the tetrad field, and you obtain the Christoffel symbols. And it is clear that the Christoffel symbols is not a gauge fixed spin connection. It does not belong to the space of spin connection. And it is clear also in that case that the tetrad is clearly not an element of the gauge group of the symmetry, if only, well, again, because of the way it transforms on the left, whereas again, a gauge element is transformed by conjugation on both left and right, but also because the tetrad in that case takes value in a group which is bigger than the structure group of the theory. You know, it's a GL4 valued, whereas it's not Lorentz. So in a sense, the notion of dressing is you know,
wider.
Yeah, in a sense, you might think that there is sort of loose overlap, conceptual overlap between the two, but technically, mathematically speaking, they are still different concepts, I would argue. And indeed, the case of the tetrad field as being a Lorentz dressing field, I think clearly shows that. So that's okay. I resume. If there is no further question on that point or yet, I resume. So that was basically the technicality of the dressing field, the bare minimum technical core of the dressing field approach. The question is, how does it relate to the notion of substantive and artificial gauge symmetries, and how can it be used to implement the criterion that we've been talking about? Well, I would say that if the dressing field is local, so will be the invariant composite fields, the dressed field that you can build, and therefore so will be the theory, the rewritten theory that exists by proposition 3. So it will remain local. So the conclusion would be that the K gauge symmetry that you've just erased was artificial, in a sense, because you've rewritten your theory, doing away with that symmetry, and yet still you remain you retain a perfectly local theory. On the other hand, if the dressing field that you are managed to build or to find are always non-local, so will be the dressed composite fields, right? And so will be the theory that you rewrite in terms of those elementary dressed variables. And so in that case, I would argue that the gauge symmetry is substantial. Right? That would be a way to operationally apply the criterion to a theory. And so usually I should warn that if you introduce a dressing field in a theory by hand, as their own degrees of freedom unrelated to the other one, those kind of dressing fields are Stuckable fields, right? They enforce an artificial symmetry. But what is tacit in the full-blown mathematical formulation of the dressing field method is that they should be built or extracted from the fields, the degrees of freedom that are already there in your theory, right? And so, for example, in the covalent phase space literature, often, which deals with the study of the gauge field theory over bounded regions, there have been, since a couple of years, people trying to introduce what they call edge modes. And those edge modes are exactly ad hoc dressing fields, introduced by hand in the theory. So my take is that those kind of objects, in the end, don't do much. But it is more important, more interesting when you can extract them, the dressing field, from the already existing degrees of freedom in your theory. So, for example, if you have a dressing field built from the gauge potential, and if you are pressed for interpretation of what that means, you could say, for example, that the dressed objects are fields that are shrouded in the gauge field they generate, right? For example, the matter field, if it is a charged matter field, you could say, well, it is, it is enveloped into the gauge field it generates, it solves. And the same for a charged non-abelian gauge potential. You can say that the dressed version of it, if the dressing is built with the gauge potential itself, you could say it is like in QCD, for example. You could say, well, the dressed object is simply the gauge field shrouded into its own gauge field it generates. And so, for example, Dirac gauge event formulation of QED of 50, so in the paper of 1955, sorry, and in the book also, reprised into his book of 1958, we have, is doing QED, so phi in this case is psi, it is a bare electron, a spinor, and the dressed object is written as a psi star. And for example, we see here equation 16, so here is the dressing, and the dressing field U is simply this phase factor here, so the Dirac phase, and it is indeed clearly a non-local object here. You see it is an integral, it depends on at least 2 points. So it is a non-local object, even though he has been using, given additional assumption, he has been finding one nice solution of this for the phase factor here in the integral, which is simply the Coulombic field generated by the point particle. And so he goes on to explain that this is quite nice, because in a sense, this dressed object, the psi star, is the operator of creation of an electron together with this Coulomb field, right? Which is kind of nice. And he goes on to say that, oh, sorry, I missed something, it seems. No? Okay. Yes. So he goes on to say that a theory that works entirely with gauge invariant operators, as its electron and positron always accompanied by Coulomb fields around them, which is reasonable from the physical point of view, which indeed I find indeed reasonable too, because it is indeed gauge invariant and physically sensible. So in that case, as we just saw, the situation is that the U1 is substantial because still the dressing field is non-local. So another example is the paper by McMullen and Lavelle. They did a bunch, but that one was a big one, in which they tried to build constituent quark from in QCD. So in that case, the dressed matter field is a dressed quark, right? So you have a multiplet of quark, and the dressed gauge potential is a dressed gluon field, exactly. And for example, in that case, again, their explicit algorithm to compute to extract such a dressing field formally is still a non-local object. So I would say that again, in that framework, their proposition, at least, show that SU3 in QCDs remains a substantive gauge symmetry. Now, other possibility is if you build the dressing field from the matter field content rather, or well, to me, everything that is not a gauge potential is qualified of matter field. So again, if you are pressed for an interpretation of this, you could say that the dressed objects are fields that are embedded in the C generated by the field phi, right? So this, of course, should remind you of something. One other way of interpreting such an object has been to say that the bare gauge field its degrees of freedom from phi. As you know, this is the case in the spontaneous symmetry breaking mechanism. At least this is how it is talked about, interpreted, which I find slightly ridiculous, but fine. Seeing this is something you can find in the literature. And so one example of this would be scalar electromagnetism, with which you can model the Aharonov-Bohm effect or the Abelian-Higgs model. And another, of course, important example is the SU2 cross U1 electroweak model, right? But in both these situations, both these examples, it turns out that the dressing field that you can find in those framework are local, right? So I would conclude in the light of the criterion we've been talking about, U1 and SU2 in both those theoretical framework are artificial gauge symmetry. So I should also stress the fact that, of course, we should realize that the judgment about the artificiality or substantiality of a gauge theory crucially depends on the field content of the theory. It is kind of obvious, but it seems something that is sometimes overlooked in the physics literature. For example, in spinel electromagnetism, U1 is substantive. So is Lorentz in spinel GR, and so is SUN in pure Young means. But they become respectively artificial. For example, U1 is artificial in scalar electromagnetism, or Lorentz symmetry is artificial in pure GR without spinel matter field. And I would argue it is also in the case of the electroic model. And yeah, I thought that to substantiate that last claim in particular, and to showcase a bit how the dressing field approach works in a nice example, let me remind you the case of the electroic model quickly. And again, sorry for those who already know a lot about this. So the basic kinematics of the model is the gauge potential, A for U1, capital B for SU2, with their respective field strength. We have a scalar field in the fundamental representation of SU2, and the corresponding covariant derivative with two coupling constants. The Lagrangian, of course, is just the sum of the Young-Mills terms, a kinematic and interaction term for the scalar field, and a potential term. Again, things quite standard. And the electroweak vacuum is found by minimizing the potential. Right? Now, what is the standard narrative around this model? It is to say that, well, we have two phases. One phase, when the parameter in the potential mu squared is positive. In that case, there is only one vacuum in the theory at the origin of the complex plane, and it is SU2 invariant, that minimum. So if you do a perturbative expansion of the scalar field around its minimum, and you insert this into the minimal coupling, you simply obtain the interaction, the minimal coupling of the fluctuation H with the gauge field, and those gauge fields are therefore just massless gauge field. There is nothing beyond the simple minimal coupling with the gauge, with the scalar field. But there is another phase in which mu squared is negative, in which case we have a whole manifold of degenerate vacuum, which is an SU2 orbit, right? But it means that any one vacuum on that manifold is not SU2 invariant, right? The vacua are mapped on each other by the SU2. So if you do a perturbative expansion around that non-zero vacuum and you put it in the minimal coupling, you obtain not only the covariant derivative and the minimal coupling between the fluctuation and the gauge field, but you have also constant mass terms for the gauge fields, right? So in fine, in the Lagrangian, these are the terms that will give you the masses for the W and the Z. And of course, the mass of the scalar field itself comes from the expansion in the potential, and the mass of the fermions will arise this way from the Yukawa coupling, as you may know. So the takeaway is that we have mass generation through spontaneous symmetry breaking, right? Whenever we select one vacua among the manifold, we obtain masses in a theory. Well, I propose an alternative way of doing the same thing, which is the following. So you extract a local SU2 dressing field from the scalar field, right? You use a polar decomposition. There is a SU2 matrix built from the element of the scalar field. And of course, the modulus is a real positive variable there. And given how the scalar field transform as a fundamental representation of SU2, you can propagate that transformation in the dressing field and check that indeed it transforms like a dressing field, right, on the left. It is a SU2 valued object transforming as a dressing field should. And so now that you have that object, local, you can build local invariant composite field, right? So you dress the gauge field. Of course, only the SU2 part is dressed. The U1 part doesn't see the SU2 transformation, SU2 dressing. And when you dress the scalar field with its own phase, SU2 phase, of course, what you end up building is just the modulus of the scalar field. And now by proposition 2, 3, you have that you can rewrite the theory in terms of the dressed variables, the SU2 invariant fields, and this will simply be a U1 gauge symmetry, right? You have killed the SU2 subgroup, you are left with only U1 gauge symmetry in that theory, and it is totally local. So you could argue, again, in the light of the criterion that we've been discussing, that SU2 is artificial. And now, if you look at the residual symmetry, the residual U1 symmetry, a very simple analysis of that residual symmetry suggests very strongly to change variables still, right? In the boson, in the gauge boson sectors, going from A to the 3 dressed B objects to extract one more invariant object, fully invariant, because we have one fully invariant, which is that one, the modulus square of the field. This is one totally U1 cross SU2 invariant object. But now you have another one, which is the Z. You have one U1 connection, the gamma, and you have 2 tensorial U1 objects, which are the W's. And you can rewrite without any efforts the whole theory in terms of those objects, because they appear completely naturally in the writing, in the unfolding of the Lagrangian. So what you have is that the physical degrees of freedom are identified from the very beginning in both phases of the theory, because notice that we have not talked about the vacua, about the potential, about minimizing it, nothing of the sort. And now what happens is that if you do look at what happened in that situation, of course the potential now is a potential for a real positive field, and the electric vacuum is found in the same way by minimizing that potential. But now in both phases, the vacuum is unique, right? It was unique in the U2 square positive phase, right? The so-called unbroken phase. But now in the so-called broken phase, where U2 is negative, you still have a unique vacuum wave, right? Because the potential is just something like that. And again, if you put the perturbative expansion around this minimum in your Lagrangian, what you obtain is the masses for the W, the Z, and the H, and the fermion, if you include the Yukawa couplings, right? So what has happened, actually, is that there is no spontaneous symmetry breaking. HU2 has been eliminated from the very beginning, purely at the kinematical level, and mass are generated through a phase transition of the electric vacuum, right? So nice example of, and you would expect that it is so because, again, by the very first step in which you are able to build a local dressing field for SU2, you knew that SU2 was artificial. So you know it cannot play any real role into the physics of the model. And indeed, you see that what is really operative in that case is really the non-zero expectation value of the scalar field.
Sorry.
Yeah, please.
Sorry, but by the last sentence, all you mean is that the expansion around this shifted vacuum, vacuum rho naught, will have mass terms, and that's, it doesn't depend on nothing eating anything. It's just writing the fields in the dressed variables or in the correct local variables with less symmetry, and then just looking at what the vacuum is, you get a shifted vacuum, and for the shifted vacuum, these terms have mass, right?
Yes, exactly. Yes, absolutely. Because indeed, that's the point indeed, that all those variables, the gamma, the W, the Z, the Higgs, the rho is what should be called the Higgs. Well, okay, maybe not the Higgs appears, but all those variables are identified before looking at the minimum of the potential. So it's just that once you look at so in a sense, the physical degrees of freedom are there in both phases of the theory. The question is, in which case you have masses, so that's controlled by whether or not you have a non-zero vacuum for the scalar field.
Adam, you also, sorry. Adam, you also have a question on this because you've raised your hand.
Yeah, thanks. So how does this relate? I've been thinking about the fact that people say, you know, there was an electroweak phase transition in the early universe. Pre-electroweak phase transition, we had all those symmetries present, and then they were broken, and this is somehow like an actual process that happens in time. At least that's sort of the standard story. Does this contradict that, or is it something more subtle?
Yes, well, in a sense, I think it does contradict that insofar as to deny the idea that what is operative is the SU2 breaking. Because in that treatment, you say, okay, SU2 was artificial anyway. You can write the whole model without ever having SU2 being operative. What you have in the end, in that stuff here, that rewriting of the theory, this is a U1 gauge theory. There is no more SU2 appearing. But what is existing in that theory, in that framework still, is the fact that you may have an electroweak phase transition, because you may indeed have two phases in that theory, right? In which you have either a zero vacuum or a non-zero vacuum. And this is what is operative. And this is indeed a phase transition. It may totally be the case indeed that in the far past, there have been such a phase transition of the electric vacuum, but it has nothing to do with SU2 breaking. That would be the contention of the.
Great.
Sorry.
Okay. Michael, you have a question?
Yeah. How do you get to a quantum theory if this polar decomposition? How do I quantize that?
Yeah, that's a very good question. That's precisely that's the last slide of the talk, where indeed you have to really convince people of this. You would have to quantize that theory, the dress theory. So you would have to have a framework to quantize the theory. But this is an ongoing research project, right, with Philippe and with colleagues. So yeah, but there are pretty encouraging results. For example, if only because, as we will show in a moment, the fact that this approach is very closely related to the so-called FMS approach, Folisch-Markus-Strachey. And so Axel knows, I've been presenting this at the last meeting. And those formulations can be put on the lattice and, you know, give simulation, and they can be quantized, at least in that way. That would be a numerical approach. And for models, for example, the SU2 model or the abelian Higgs model, you can do exactly the same, and you can quantize the model, and it works perfectly well too. So I have no final answer, encouraging data points, I would say, but indeed, it is still an open and very important question to lay down a framework for quantization of the method.
Yeah, I mean, that goes back to the days when I tried to understand that in my diploma thesis many years ago, and everybody said, yeah, go on the lattice, but that wasn't popular in that sector of physics department in Vienna, and I couldn't do it on the lattice. So I think I think that seems a fascinating approach, but a lot of people said, yeah, maybe only on the lattice can one get that.
Mm-hmm. Yeah. Well, we see that there is, well, precisely, that's a good segue maybe to my next slide, because I think what I have next is, yes, I have the fact that just to show that this is in some sense, at least this treatment of the dressing field by dressing.
May I just interrupt to give an answer to that question?
Yeah. Sure.
Indeed. I mean, from the point of view, from a path-integral quantization, the whole thing is like a change of variables. And so at least without the U1 part, this has been explicitly done for the SU2 theory in like the early 80s in lattice calculations. What happens is that this has a non-trivial Jacobian, which creates additional terms in the Lagrangians. But if you take this into account, then actual lattice simulations have been performed in this way, using exactly this formulation of the theory. And indeed, you get exactly the same answers, at least in the Higgs region, than with the usual formulation where the gauge symmetry is not eliminated by such a variable transformation.
Yeah, Amanda commented from this idea that this probably ends up in non-regular representations. That's how Turing was thinking about that, and I think there's a paper by Strachey where he also says that this has to do with non-regular representations. So anyway, which is kind of what constraints are, and then the question is, what does this mean quantum theoretically?
And actually in the 90s, there had been, as Jordan said, in principle, you can do perturbation theory around this theory. And indeed, in the 90s, people have compared the full lattice version with this perturbative approach around this, and at least for parameter points inside the Higgs region, they found very good quantitative agreement between both approaches. So if you perturbatively quantize it, or you which actually eliminates the Jacobian, or you are doing a full non-perturbative quantization with lattice methods, both of them agree within the precision of the actual technical lattice simulations.
These extra terms that you get for the Jacobian, are they local in the original variables?
Yes, well, they're not, well, originally don't exist, but in the new variables they exist, but they are not power countable, renormalizable. So essentially, what you get is the logarithm of the term which is logarithmic in the new field rho.
Okay. Thanks.
Yeah. That's so indeed. So again, thank you for the contribution to the discussion. So I just wanted to highlight the fact that this kind of treatment of the spontaneous symmetry breaking model, which I would classify as dressed versions, are not so new in the end, because already in the work of Higgs, for example, 66, it was a year before the electroic model was proposed. We can read that, for example, he says that, yeah, it's possible to rewrite the theory in a form in which only gauge invariant variable appear, right? So here it is, for example. So 22 are the dressed object, and the theta is exactly the phase of it was an abelian example, of course, a model. He was treating an abelian model in that case, but theta is the phase of an abelian dressing field, for example, right? Transforming on exactly as a dressing field should on the left, and you exponentiate those. And the equation 23 is exactly an example of a dressed Lagrangian, right? Again, in the U1 example, U1 case. And we also, and he was also optimistic, trying to show that this correspondence between the bare Lagrangian, so to speak, and the dressed 123 extend to the corresponding quantum mechanical operator. So again, relating to the question of Michael, that was good hints, good positive data points, at least for an abelian Higgs model, so to speak. And we have also the same kind of proposition in Kibble. Again, it was shortly before the proposition of Weinberg's model, in which he shows that it is perfectly possible to describe it being the non-abelian spontaneous symmetry breaking model without ever introducing the notion of symmetry breaking. So the Lagrangian 66 that he's talking about is the dressed Lagrangian, right? And he rightly pointed out that it is indeed to the dressed Lagrangian that experimental data would point to, right? But he said, okay, maybe the only advantage of the gauge version, the bare version, would be that it might be regarded as an advance, right? Because we would remark that there are a high degrees of symmetries in the interaction given by this Lagrangian. So in my view, it is either a great advance, perhaps, or a puzzling accident, right? Since if SU2 is artificial, what this high symmetry points to is that there may be there should be a deeper framework from which that approximate symmetry stems from, right? So it should give in some limit, some effective limit, something like an artificial SU2 symmetry. So anyway, just to show that it was still pre-electroic model, all those discussions. But then, of course, it became much more important once the electroic model was effectively proposed and shown to work. And so, for example, to give you a still more example of the appearance of the dressing-like things happening in the literature. You have this paper by Banks and Rabinovici, in which they explicitly do a polar decomposition again of the scalar field using omega as what I call a U, the dressing field, and obtaining the dressed B field, the dressed non-abelian field in that case, right? So that, okay, again, that's a slight abuse of the covariant derivative, probably notation, but still, it's just the inhomogeneous dressing of the omega stuff. I think it should be
Okay, so Enrique has raised his hand. So Jordan, if it's okay for you, maybe Enrique.
Yeah, sorry, I didn't check. Yeah, thank you.
No, it's fine. If you have, not much to go, I can wait. Or
No, please go. I have still a bit of discussion too.
Okay, so just following up on what we were saying before, if you have if you have an artificial gauge symmetry, which you have, I mean, first off, you need, it's an existential claim in the way in that there exists some dressing field, let's say, made up from the fields that for which the gauge symmetry is artificial, right? It's not. It's something that. Or can you assess whether there will be such a dressing or there won't be, or is it like trial and error in a way? Like, can you ever state conclusively that a symmetry is artificial or substantial? That's the first component. And then the second component, let's assume that the symmetry is artificial. Is it guaranteed that the Jacobian in the path integral, for example, will not be like some kind of non-local operator, or will be some functional determinant of something that you need? So the question is whether this artificial and substantive distinction survives through this quantization procedure, whether the locality properties, if you have eliminated variables that are artificial, so you remain with local variables, if the Jacobian will also preserve that kind of locality or not.
Right. So to the second question, I admit I cannot answer conclusively. First, because again, the whole interplay between the dressing and the quantization stuff is still an ongoing discussion, ongoing project, and it's not settled by any means to me, clearly. Okay. Even though there are different ways to try to answer this. For example, depending on how you mean when you say that, okay, a dressed field theory should be equivalent. Sorry, the quantization of the dressed field theory is equivalent to the quantization of the bare field theory.
But I mean, I think my question is a little bit simpler. I don't. Yes, I understand that the quantization is not understood, but my hope was that at least for the path integral measure, you get this Jacobian for this change of variables, and that the Jacobian itself would follow the properties of the classical assessment, or it would obey the classical assessment. But
yeah, I would hope so, but precisely what I wanted to say is it were perhaps not far off what your question is, because I was about to say that I have a broad argument that, okay, not fully fleshed out technically, but I hope it might be at some point, is the fact that, when you have a theory, gauge theory, if it preserves the gauge symmetry of the classical theory, you are anomaly free. So you see that the gauge transformation of the measure of the path integral doesn't give rise to anomaly, to stuff like this. And I would expect that the kind of transformation of the measure that arise from the dressing field is at least superficially or formally akin to that, I would say. And so I would say if you start from a theory which is free of anomaly, of gauge anomaly, local gauge anomaly, consistent gauge anomaly, I would expect that somehow maybe there is a way to ensure that what happened to the measure of the path integral is handled the same, meaning that there is no dressing anomaly, so to speak, right? So that there would be, and so in that case, yes, you would have somehow whatever you say about the verdict you had about the artificiality of the symmetry at the classical level would survive at the quantum level, something like that.
Right. Yes. I think it should be almost trivially true. But anyways, let's talk later.
Yeah, but exactly. That it seems a convincing argument like this, but sometimes you're surprised by the technical details. So I just provisionally raise it, but not saying that it is conclusive. And toward your first question, indeed, the question is, can you always conclusively be sure? Well, I think I've already or in particular, you've heard me say this. Maybe I would say that indeed this strategy is kind of asymmetric, because you would say, okay, at the moment I find at least one local dressing field, I can be sure the symmetry is artificial. Again, sure, quote unquote. But on the other way around, at least in principle, we say, well, I have to suspend judgment. Maybe someone more clever than me could find. I only found non-local ones. Maybe someone more clever than me can find a local one. Okay, in principle, you could say that. I would say that in practice, the options are always quite limited, perhaps.
Yeah.
For example, if you have a theory with only a gauge field and a scalar field, for example, you don't have there is only a finite, discrete amount of possibilities to be checked, I would say. So in a sense, if you didn't find anything that should maybe count as conclusive proof of that the thing is indeed substantive, right? I've checked everywhere, checked all these possibilities, and I don't find any. But okay.
I mean, intuitively, intuitively, this should also be provable in the sense that if you have fields that transform without derivatives, so transform algebraically, like the scalar fields, then presumably you can find a dressing field that's completely local to have the properties that you have. But if something transforms to a derivative, then if you're only going to use that for the dressing field, then you need to invert this derivative in some way, which is an integral, which is then non-local.
Yes,
or something like that.
Indeed, there is that technicality indeed that should help, but it may also be that, for example, in the case of, I would say, the case of, well, not exactly that, but there may be a situation in which, even with fields transforming more, as representation algebraically, it may be that still you cannot extract the right object from that. For example, if you just my favorite case would be, for example, but okay, that's a discussion we'd have also, the two of us, is the fact that I would think that in the case of spinors, for example, it is not clear, for example, spinor in general relativity. If you try to extract a Lorentz dressing field for a spinor, you cannot use the tetrad. The tetrad is GL4 valued, so it is not. So a spinor is not a representation for GL4. So you would have to extract a Lorentz matrix from the tetrad to try to dress the spinor, for example. And maybe this you can do locally with very constraining situation, but it's not not globally defined, for example.
Okay.
So it might be that it might be that there are a bit unfriendly technical obstruction for you to extract exactly the nice and globally defined object that you would like to obtain fully globally invariant object. So it's indeed, as you said, it's indeed a case-by-case situation, really asymmetric. So yeah, and so yeah, I was just finishing a bit on this, showing the in that case again, just after the electric model. You got the just Lagrangian. We are here also quite often what I would call a confusion between dressing and gauge fixing, as it is often the case. And then after that, yes. So after that, you have, of course, the very famous paper by Fraulich, Mark and Strachey. One of them, there is another one of the same year, I think, or the next year, in which they very soundly propose that we should try to find a description of gauge in terms of gauge invariant field operators, and they give a list in component lists, and so we could recognize that those three variables, for example, this being the Z0, are component of the addressed gauge fields, that those two would be the component of the addressed fermions, left fermions, and this is just the modulus of the scalar field that we had in my demonstration just before. So clear link between the FMS construction of those field operators and the more geometric, so to speak, approach coming out from the dressing field approach. And of course, there have been since then a lot of people rediscovering that kind of treatment, right? Not always for the same motivation, not always from the exact same modeling, but it's often very close, right, to rediscovering the same polar decomposition and elimination without symmetry breaking. And so we can find many of those references in Axel's very nice review from 2019. And the same year, I did myself elaborate a bit about this artificial versus substantive gauge symmetry stuff. And but again, it was more philosophy of physics oriented, and precisely in the last 20 years, strangely, it's more often philosophers of physics that have been interested into, well, not strangely, in the end, I've been interested in these, starting in paper by Hermann in 2004, and then many other authors have been rediscovering for themselves this trick, this decomposition, this SU2 elimination, and engaging with what it means for the interpretation of the electric model in particular. So it's perhaps worth reminding what Hermann was saying at the time, in that 2004 paper, saying that what is exactly accomplished is hidden behind the veil of gauge redundancy. The popular presentation uses the slogan that the vector field has acquired its mass by heating the Higgs field. You know my sentiments about this interpretation, but it is a direction of duty for philosophers to repeat the physicist slogan rather than asking what is the content of the reality that lies behind the veil of gauge. And later in the same paper, he says it does suffice to plant the suspicion that when it is lifted, the veil of gauge, what is revealed is that the Higgs mechanism has worked its magic of suppressing zero mass modes and giving particular mass by quashing SSB, spontaneous symmetry breaking, right? And he said that, well, confirming the suspicion or putting it to rest required detailed calculation, not philosophizing. So at the time, he was advocating to try to work out the electroweak or Higgs mechanism through the constrained Hamiltonian system, if I remember correctly. Here I hope I may have perhaps convinced you that through the dressing field, there is a quite simple and natural way to do exactly that, right? To challenge at least the prevailing narrative around the SSB in the electroweak model. So that was an example in which the dressing field shines a bit. And I wanted to finish this little presentation with a word about its extension. As I said, there is application to the gravitational physics regarding local Lorentz symmetry. There are applications in twistor theory, in conformal geometry more generally. And recently, there is an extension to diffeomorphisms, right? Which is, of course, if you are to do gravitational physics, diffeomorphism are an important local symmetry too, not of the Young-Mills type, for which the dressing field method has been developed primarily. But so extending it to diffeomorphism has been a long time coming, so it's finally here. As of this month, I have posted on the archive a preprint on it. So what would be a dressing field in that case? So it would be a map, a diffeo from some model manifold N to M, your quote-unquote space-time, and who is defined by its diff M transformation, which is as is specified here, again on the left, notice, which is of course natural since the target space of the dressing field map in that case is the base manifold. So the diffeos act on the left, and the -1 here is a conventional. And then what you can do is build, once you have a phi, so phi in that case is not a matter field as it was in my previous slide. It denotes a collection, a field variable of any kind, gauge potential, spinor, scalar field, your metric, whatever kind of tensor field you like, or a collection of them, right? Often I think of it as a collection of them. And in that case, the dressing of such object or collection of object is simply defined as the pullback by such a map, right? That's the technical equivalent of the dressed variable we've seen up to now. And again, for field dependent dressing field, right? So that would be maps from the field space to that would give you such a homomorphism. We have a natural relational interpretation of those objects, right? Because in that case, you would say that the dressing field, the field dependent dressing field, gives you a reference frame provided by the degrees of freedom of the field. And in that case, the dressed field will represent the physical degrees of freedom relationally defined with respect to each other, right? So for example, if phi has two elements, is a couple with the metric and a scalar field, for example, you would say that your phi would be simply your scalar field, giving you the scalar field could be a dust field or a true scalar field, why not? But for example, a pressureless dust particle field, for example. And this would give you a preferred reference frame. In cosmology, for example, that would be exactly the case. That would be the co-moving, co-mobile reference frame of the galaxies, for example. And therefore, the pullback, now, if the pullback of those fields, if the other field is the metric, you have the so-called scalar coordinatization of the metric by the dust field, for example. So those kind, all those I would say this literature preoccupied with this scalar coordinatization from the 60s to the more recent falls into the technical framework laid down here. And this is called, for example, in the terminology coined by Rovelli, this is called a complete observable, right? So the phi, the bare phi, the field would be called partial observable, and the dressed one would be called complete observable. And so I remark that in that case, there are such a thing as dressed integrals, which is simply the integrals of functionals of dressing field. And they naturally involve the definition of dressed regions, which are diffeo invariant. And those objects would represent the physical spacetime, right? Again, M is not spacetime, as people familiar with the history of general relativity and the whole argument know. M is not spacetime, but in that case, the dressed region could be understood as a region of the true physical spacetime. So in that case, the dressing field approach in that framework formally implements the Einstein point coincidence argument, right? Again, I don't know. Let's see. For those who know, it was these ideas that indeed this was Einstein's answer to his own whole argument to try to understand the meaning of diffeomorphism in general relativity. The observation being that what is physical is the coincidence of the value of fields or the crossing of two word line of two particles, because this crossing is indeed a diffeo invariant statement, right? And so this is what is physical degree of freedom, and this is what instantiates a physical spacetime event, right? So the point of the underlying manifold are not physical. What is physical is the coincidence between field value, and this is how spacetime is to be defined. So this is a new development, new preprint. And to finish, I will say probably, I hope I will have the opportunity to say more about those things in the next meeting. But for now, I will stop just pointing out that there are, of course, a bunch of open questions that may be addressed. For example, the generalization of the method to supergeometry with application to supergravity, or to higher geometry for application in string and M theory which is replete with models with various symmetries, and it's sometimes very hard to understand, okay, what is really physical, what is formal artifacts. So it would be nice to have a generalization of the dressing field method to those contexts, which would provide a lens through which to try to analyze a bit the possible physical content of those models, those theories. And as we've already said, of course, the formal quantization of dressed relativistic gauge field theory would be an important step to take in the development, to either to see, as Enrique has been pointing out, how robust will be the demarcation between artificial and substantive gauge symmetries. Does it survive? It is quite robust in the classical level. Is it as robust and useful in the quantum level? That needs to be assessed, of course. Lots of interesting questions there. And if the dressing field approach is to be a reliable tool, of course, it should be confronted to the whole quantization procedure. So, but this indeed is a key concern for many of us here. So anyway, thank you. I stop here. Here's a bunch of reference, and I'm open to still more questions if you have any.
Okay, thank you so much. This was wonderful. We already had a couple of questions, but now we have like official time for official questions. Axel, you were first to raise your hand.
A couple of remarks.
Yeah.
So first of all, know that there exists possibilities how we can formally eliminate also diffeomorphism from even quantized versions of general relativity, at least in 2 dimensions.
Mm-hmm.
Again, in a lattice construction, these are these dynamical triangulation approaches, which in 2 dimensions you can show it exactly. In higher dimensions, of course, it's a bit more conjectural. So that's a thing. The other thing I wanted to remark is concerning supergeometry. So at least from the point of our approach using this Fourier-Markov-Strachey, we have seen that supersymmetry in relativistic field theory actually works. And it stands to reason that it's also working in supergravity, allowing you to eliminate in any gravitational theory that includes our universe supersymmetry entirely from observables. So prima facie, supersymmetry can never be observed.
What do you mean exactly by that?
But the point is, if you want to have supersymmetry,
mm-hmm.
and you want to have gravity,
yeah,
supersymmetry is automatically a local gauge theory.
Yes, I agree.
And that means that anything that if you can eliminate gauge symmetries, even in that case, any observable cannot exhibit supersymmetry.
Yes. Okay, but presumably you could still, because if you start with a theory which would have let's say, well, okay.
In that case, the distinction between a particle and a superpartner is exactly the same as between a red and a green quark.
Yes. Yeah, I see what you mean. Yeah. Interesting. Yeah.
I made this argument in some paper already, but it's not something which is worked out. But we were working on an FMS approach to the supergravity case.
Yeah.
Precisely show how the low energy spectrum is, or the physical spectrum then doesn't show supersymmetry anymore. Yeah,
fantastic. Yeah, good. So that makes things that we can discuss. Fantastic.
Yes. And the other thing concerning the quantization procedure, I think there are 2 important questions. I think it's relatively straightforward what you need to do if you take the, as Enrique said, if you introduce your dressed fields after quantization, I don't think that there is any substantial problem with that. Because it then essentially boils down to a variable transformation, and the rest is more technical. Proving that this gives the equivalent to first doing that and then quantizing, that may indeed be more complicated, but the question is,
that's a square commute. Yeah, I agree.
So and finally, of course, my personal remark is from the point of view of physicist, as me as a physicist, for me this distinction between artificial and substantial is probably not particularly relevant, because quantum physics is anyhow non-local. So for me, of course, I still don't think that this is an important distinction, but of course, it's something which needs to be, which is a more philosophical question. I agree.
Yeah.
So far, my comments here.
Thank you.
Okay. John, do you want to respond to this, or should we go to Michael's question?
Well, no, I think I kind of was more remark than question. So yeah, I think it's fine.
Perfect. Michael? Michael, we don't hear you. At least now you're muted. You're muted.
Yeah. A philosophical story that you told. I was in Ehrman's presidential address in Milwaukee. It was anyhow a strange address where at the end of the day he really said, yeah, just quotient it out, and we don't want descriptive fluff. But that was kind of ridiculous for me, because since I had written my diploma thesis on that, I knew how difficult it was, whether you go Hendo Teitelbaum or the things that Turing was doing, that's Grundling-Hurst's work. And I'm pretty sure that's also in this, Strachey knew about that you cannot simply quotient out stuff in a naive way. And I think what in this 2012 paper, I didn't really say so loudly. Maybe that's Struve, who is typically read, oh yeah, you can do Ehrman's program. There's a passage where Struve writes all the nice things about Ehrman's program, and I said, yeah, well, but we quantize with infinite metric. And so there's this kind of dishonesty in the paper, or honesty about the physics. And that's why I'm really convinced that the quantization is the essential point, because Struve, this paper implements all the niceties of the program, which are obvious on the classical level. But if you go into quantum mechanics, it's very different. And Struve doesn't give us a solution. He just say, yeah, let's do Gupta-Ploiler as everybody does that. And that's the second part of the paper. So the paper actually tells us that it doesn't work in that simple fashion. And that's what I find rather attractive in this discussion here, is that one says, well, be it on the lattice or not, or being with somewhat other approaches, one tries to go to the proper quantum theory, because the naive philosophical intuition obviously doesn't work. So that's how I read this history from Ehrman to Struve.
I see.
I mean, you just look through the paper when he then starts talking about the quantum theory. Yeah. I mean, I said it in my paper, but I didn't say, I mean, at the end of the day, you want to get this stuff published in philosophy. I didn't say this is kind of dishonest, or honest, as you wish. Yeah, it's not the solution. The issue is, how do you quantize that properly? And I mean, my argument wasn't the addressing field method, that I just didn't know, ironically, even though I heard talks from Strachey at Trieste. But that if you go in this constrained Hamiltonian dynamics, and you see that's anyhow totally complicated, and so you cannot simply naively quantize out. And so you have to make decisions, and that's the debate that you had. It's an important one. I mean, what are the essential symmetries? So the debate that you had exactly with Axel Maas, these are all the debates you have to solve, or have to take a stance to get to a quantum theory that makes philosophically more sense. So that's my 2 cents here.
Yeah. No, yes, and indeed, in a sense, that's also my feeling there, is the sense that presumably it might be, well, possibly it may be something different to try to quantize a theory who has a substantive gauge symmetries, because they encode something physically important, or seems to, whereas quantizing a theory with a completely fake theory, because of course that's the Kretschmann objection, right? Given any theory, you can always add structure, spurious structure with new symmetries that at the classical level that plays no role at all in encoding any physical information, and you can try to quantize that theory. But the question is what you obtain then. Where is the physics in that stuff? And so the question is indeed, I would say you have a square, right, between you have a theory with or without symmetry, and you try to quantize, and the question is the square commuting? And yes, in the case
anything that's more perspicuous than these 8 levels in Henner-Teitelbaum, what you do with first, second class constraints or whatever, is most appreciated.
Yeah.
Okay, Enrique.
Sorry, I was looking for the. Lots of comments. But let me just propose perhaps a different criteria for distinguishing symmetries from, although I don't know how far this could be taken, but usually, if you think of the Stuckelberg trick, the point is, it seems to me, that if you just come up with add any symmetry to a theory that didn't have that symmetry, there will be no real coupling between these these new fields. Let's say there will be no how do I say this? There will be no coupling to conserve charges that you had before introducing the fields. There will be no consequences for the conservation of charges before you had introduced the fields. It seems to me that it's also a physical criterion where the Stuckelberg fields, they can be somehow interpreted as fields sourced by charges in some way. And so I'm just wondering if, first of all, if that could be made sense in this context, because we do, there is some relationship between here, it seems to me that these fields that have these fields that you could not use to build the local dressings, they represent long-range forces, it seems to me, even though, disregarding confinement, but they're like they're gauge potentials or the gravitational potentials or gravitational field and so on. And the ones that don't represent long-range forces, that would represent the interaction of charges and so on, like things that transform locally, like matter fields, they can be used to produce local dressing fields. So anyways, this is just a very, very hand-wavy and suggestion about how to relate this mathematical criterion, which I think is very useful and nice, to something that could be interpreted in a very straightforward physical fashion. And the second comment that I had was about this one concept that I always found missing from the Rovelli complete observables, and I think perhaps it is missing here too, at least for the cases where the dressings have to be, well, let me put it this way. Suppose you have a field space that has two kinds of fields. Let's call them A and, I don't know what's the other field you call it, psi, phi. No, phi is the full thing. So A and psi, but you could have G and something else, and psi as well, which is a matter field for GR. So you have some field space like that. But now suppose that these are not coupled. That there's just no coupling between A and psi or G and psi. Let's just stick to one so it's not confusing. So A and psi. So these are not coupled. Now, what are the orbits of the gauge orbits of this bundle? If you think of it, let's think in the diffeomorphism case, it's unambiguous. The orbits of the space just are, you apply the same diffeomorphism to G as you apply to the scalar field. So you apply the same, you shift along G and psi together. And so these are the orbits. But what does that mean? that means that if you apply a diffeomorphism just to G and not to psi, you would be in a model in a different orbit than G and psi. So let's call it, GF or F star G, and psi is in a different orbit, is physically different than the orbit where you just have G and psi, right? But now, if you find a dressing for these things are uncoupled. If you find a dressing that just uses the psi field, this won't really help finding what you called here. Well, sorry, I think it's in a different slide. You got relation of the physical degrees of freedom, right? So now there's something weird because you've implemented this field, which is completely, it's like a ghostly field. It's like a fairy field because it doesn't couple to the metric, let's say. But you're using it to form a dressing to fix the diffeomorphisms in this way. And tell me what points, of the manifold are, regions of the manifold are. By the way, I agree with all this point, and I have a paper with Jeremy Butterfield about this. I can send it to you. I think it very much agrees with what you're saying here, but it has this extra point. Anyways, and then you have this dressing field, but note now that I wouldn't say you have physical degrees of freedom because you're still allowing, you still have the whole argument, the whole problem here, because it's still physically possible. The two distributions will still be dress distributions. You can still write down, a G and a diffeomorphically transformed G. They're still perfectly allowed because they live in different orbits if these fields are uncoupled. And then the point is, well, do we really mean what do we mean by a physical observable? If the fields are uncoupled, if the thing that you use for the dressing and the field that you're addressing, they're dynamically uncoupled, then you haven't really obtained gauge invariant observables in the sense that we wanted, in the sense that we would have liked to have them. Because in effect, you have doubled the symmetry, even though not formally, because the orbits are still just the orbits given by the gauge transformation group, but you have doubled the symmetry because the two fields are uncoupled. So you are allowing fields in which you transform one of the fields, you're allowing configurations in which you transform one of the fields but not the other, as still possible, dynamically possible models or dynamically possible field configurations. And so you have in a way doubled the gauge symmetry, but your dressing or your connection here only eliminates one of these copies of the gauge group. And so I wouldn't say that you have the physical, I wouldn't say that you have gotten the physical degrees of freedom if you don't forbid the existence of these models, if you don't have the thing that you're using for the dressing here in this case be coupled to the physical field, let's say, the physical fields that you want to dress.
Yeah, I think in a sense I agree with you, because this is something I also say somewhere in the recent draft, the fact that all those models that contains, because of course the issue of DFO is not is not in isolation to be understood. There is also this interplay with the so you speak about coupling of fields, other would talk about the fact that they are or not dynamical. But
I mean, you could. I only demand that they're coupled because, for example, you don't need to have back reaction. So you could write the Donder gauge, for example, as just as a condition on a scalar field, which uses the metric. So it's a D'Alembert of the scalar field of this four scalar fields equals 0. So and then you think of this as an actual 4 scalar fields on the manifold, establishing which point is which. And in this case, it's clear that they are coupled because you're using the metric to determine what the solutions of these equations are. But you don't have to also have an energy momentum tensor for these scalar fields to go into the Einstein equation. So I think they're slightly different questions. But in any case, I would demand that whatever used for the dressing field has, if you're going to allow it to correspond to some to have its own configurations, let's say, to correspond to a physical field, which I think is, as you said, it is the more interesting case. Then you also need to demand that this physical fields that you're using for the dressing are coupled to the fields that you want to dress.
Right.
Dynamically coupled or whatever.
Yeah. Indeed, I'm not sure. Okay, I have to think perhaps a tiny bit about this, because the way I approach the thing is to start purely kinematically, saying, okay, or to say, at least for what I would call a general relativistic field theory, you do not have background structures first. For example, when you said an example where you have a field that would not transform under DFAOs, for example, that would count for me as a background structure. Something.
No. But forget about background. So let me just ask you this. At the kinematical level, you have.
So everyone should transform in my way.
Sure, but look, is it in your field space?
Yeah.
Is there a field? Is it a distribution of fields that corresponds, given any g and any phi? Is there a field in there that corresponds to f star g and phi if they're uncoupled?
No. Well, okay, not in the way, because for me, every field is a tensor on the manifold, or some field.
H is just another tensor. H equals f star g is just another bona fide Lorentzian metric, 0-2 symmetric Lorentzian tensor on the manifold. You don't need to consider it as f star of g.
Yeah, no, I understand. My point is that I would consider that any point, since my field space is constituted of, I don't know, any section of bundle over M, any DFO of M lift into any DFO of M.
I understand that. I understand that. I understand that your diffeos will act on both. If you're thinking of the orbits, if I give you a G and a phi, a diffeo will have to act on both. That's the orbit. I understand that. But I'm asking you a different question. I'm asking you.
Yes, you're asking if there is. Okay,
I give you a different distribution that I'm calling H. H and phi also is in this big field space, right?
Yeah, I see what you mean. Yeah.
But now H can be f star of G. Why not?
Yes.
And so, that would be in a different fiber.
Yes, I agree. Well, but I guess the point is that, okay, indeed, you could imagine, for example, having, I would have to, I'm not sure, but admitting, does it do anything for that? Both of them would still be acted upon by another DFO, for example.
Yeah, sure.
Yeah.
The H and phi have their own orbit. Yeah.
But so I think by now I think I agree with you with your remark. Yes. Yeah. Cool. And also to your first question about the charge, indeed there is something for me to be said there, because indeed if you look at the theory, for example, in which you can base the whole symmetry, you had charge. Well, by Noether theorem, you had charge before that you don't have anymore. So I would say that physical charge has to be somehow found in a way that is not via the Noether approach, but maybe extracted from the field equation, for example.
Right.
Cool.
Cool.
Yeah.
Sorry. I feel very conscious that I'm hogging the mic here, and Axel has been waiting for a long time.
Oh. So Axel, you have a follow-up on this? We don't hear you, Axel. We don't hear you. You're muted.
Sorry. There's been a lot of discussion about dynamics, but if you go through the discussion, at no point ever in the whole dressing field approach you ever needed to talk about the actual contents of the Lagrangian or even the existence of a Lagrangian. Every statement is purely based on
the kinematics.
Not even on the kinematics. It's purely based on, okay, I have these fields and they have this kind of representation for that symmetry. That's all.
Yeah.
The question whether a
Sure, I agree with that.
Substantial or artificial is at no point answered by looking at anything dynamical. It's all in the fiber structure, group theory, however you want to call it. So I think that indicates that this whole question is a purely structural question about field content, not something about the underlying dynamics of the theory.
Yes, but what I mean is there is a further question here, which I think has been overlooked. And that is the question. So I agree with you. I agree that that the dressing field method, the way to eliminate things, it works kinematically, works just at the level of field space. But there is something that has, in the case where one of the dressing fields is taken to be a scalar field that has its own configurations and so transforms as well, there is here a question about what is this kinematical field space and what is it that you do when you dress this? Do you really eliminate? Do you really eliminate what you sought out to eliminate? Do you really eliminate the full the full redundancy with respect to a certain gauge symmetry that you sought out to eliminate, or have you eliminated just, let's say, a copy of it, because now you have, because of these fields are unrelated to each other, you have in fact now allowed you have doubled your symmetry. So it's a little bit like I've added a completely ghost field configuration, like it's not ghost, sorry, ghost is a very bad choice of words. A completely like fairy field, a ghostly field, to my field configurations. I have no physical interpretation for what it is. It's uncoupled to all the other fields, and I postulate some transformation properties for it under the gauge transformations, and now I have this bigger field space, this bigger kinematical field space, but I can still use this ghostly field, this fairy field to find a dressing, but I will eliminate a copy of the gauge group, but I haven't really, I can't, if you think in terms of relational, like you said here, it can't really be used relationally to fix the other degrees of freedom, because it has no relations with it. It's ghostly. It's a fairy field, and
it's the Newtonian spacetime, so to speak.
Yeah, something. It's so I think that, and I think Rovelli also overlooked that in his partial and complete observables, because the same problem crops up there. In any case, so anyways, I think you're right. Sure, it is a kinematical question, but there is a further question depending on how you plan to implement these dressings.
But I think I agree with the spirit of your remark in the sense that indeed, okay, from the strictly kinematical point of view, you would say, okay, I have all a collection of fields, all transforming in synchronicity, so to speak, under the symmetry. They all support the symmetry, and you could indeed at least formally write invariant objects purely mathematically. The question then becomes, okay, how much of these truly corresponds to physical entity or to physical variables? Because indeed, if you have a field that is uncoupled to anyone, in principle, you could say, well, sure, mathematically, I can use it as a frame of reference, as a coordinate system for everyone else.
Right.
And it looks like I have indeed given a invariant formulation of my framework. But as a matter of, again, now physical fact, operational fact, if I have no access and no coupling of any of my other fields to that underlying fields, that's why I was talking about the Newtonian spacetime, because it's exactly the kind of role that the Newtonian spacetime plays in classical physics, right? It is something that is there to coordinate everyone, but there is no way to access it for real, right? It's so in a sense I think I agree with at least the spirit of your question. If I sorry, Axel,
honestly, the discussion very much reminds me about how spin connection in classical GR works, where you can either eliminate it by removing torsion, or you can make it a dynamical field. And depending on what you do, you get physically distinct theories, which has different symmetry contents, different dynamical contents, but nonetheless, as long as you don't couple anything with spin to it, there is no field argument how to distinguish both cases. So really, the dressing field here really sounds to me a bit like that.
Interesting. Interesting. I think we should discuss this more. Actually, not now, because it's almost time to end this, I guess, and I need to go. But I would love to discuss this further.
Yeah, me too. I agree.
Yeah, I agree. This is super interesting, and we definitely should catch up on all of this. As always, we'll be in touch with details for the next meeting. But are there any questions now? Also so we're very close to the end of this session. But are there any questions any of you wants to raise? Probably some of those who have not yet had the opportunity to participate in the discussion. I mean, like I said at the very end, and I don't want to, but maybe you could, John, you could elaborate on some of the philosophical ontological implications, like in your draft that you published on Archive. You mentioned that this is like a manifestly relational picture, right, that you want to promote, or that you think that this promotes. And here, this slide that we have discussed now, this final slide, this very important slide. You say that the phi u, represents the physical degrees of freedom, and that this is to be relationally defined. Could you a bit elaborate on this? What you mean by relationally defined? What it means for the questions whether systems have intrinsic properties, what exactly are the fundamental objects in the theory, and so on.
Yeah. So indeed, in that context, it's really I relate. Okay, this idea of this interpretation of the formalism was driven by the reminding a bit of the indeed complete observable rivalry, and also going back to the paper by Norton and Stacker in the 80s about because I think John Stacker is the one who named the point coincidence argument, the way it is named now, and in a sense the concept of the relational, it really boils down to coming back to what seems to be understood as a key insight of general relativistic physics in the end, because as maybe many of us know, so one thing that stopped Einstein on his track in developing GR was the whole argument thing. Okay, it seemed that requiring general covariance and differential invariance was physically nonsensical, because you say, if I have a field configuration over a regional spacetime, so if I simplify a bit the thing, so if I have a field configuration on gravitational field, typically a metric on spacetime, on some region of spacetime, and I drag it very diffeo, I will now have the theory the theory will not be able to make the difference between those two situations, whereas they seem to be physically very different, because I have some field configuration over a region of M, quote unquote, spacetime, and now I have a zero configuration or something like that. And so it's after the rejoinder or the point coincidence argument, when he did realize that no, actually this is still physically meaningful, because indeed you don't have access to the underlying manifold M to the point, but what you do have access to is the relative field configuration. So I think in his example was the thinking about the two particle crossing, interacting at some point. So at least, and so that crossing defines an event. It happens at some place, at some time. But precisely that event is the thing that coordinatizes the event, so to speak. The underlying manifold is just here to bootstrap your abilities. It's kind of a meta coordinate system, so to speak. It's just there to bootstrap your ability to describe things. But in the end, like a coordinate system, it disappears, so to speak, via DFO invariance. Because indeed, when you move by DFO, you move from one point of the manifold to the next. But you would drag along those two configurations, those two word line, and you would not change what Einstein called the topological fact, meaning the fact that indeed that interaction that will not be changed by a diffeomorphism object. And so, yes, the idea was that indeed the degrees of freedom, or in that case, it was the point of space-time are identified, individualized by relationally, by the respective value configuration of fields on top of each other. And so in a sense that seems to be the key, at least to me, what I understand now, it's one of the key insights of general relativity. The fact that that's one way to abolish a background structure that would be non-dynamical, non-relational in a way. Everything that is non-relational is non-physical. And so the idea is that any degrees of freedom is always ever defined in a relational way. You can only define, not only degrees of freedom are defined with respect to one another, but they also evolve with respect to one another. And there is no background absolute structure which will give you always the independent and moved and non-relational structure with respect to which you will coordinatize everything else, degrees of freedom and their dynamics.
And I would say in the gauge case, you should also think, not only in the GR case, I think you should also think of it as relational. You're thinking of, some matter field, let's say, that has a phase, and you can define other things with respect to the phase that it has. It's all these things I think should have,
I fully agree. That's exactly the thing that I think both the general relativity principle, so to speak, okay, the diffeomorphism invariance and gauge invariance to me are both, okay, they are heuristic by which you identify two symmetries, so the diffeo group and the gauge group and in both cases, they are the technical counterparts of the kind of philosophical or ontological statements that things are defined relationally. So yeah, that would be the two-faced coin. The philosophical ontological face would be the relational definition and evolution of the degrees of freedom, and on the technical face of the coin, this is implemented technically, mathematically, by requiring those symmetries.
Mm-hmm. Yeah.
So at least this is how I understand things for now. Again, in the classical framework, and at least.
No, I agree. It's also my view. Yeah.
So in a sense, I tend now to speak of relativistic gauge field theory together, and insisting on the fact that local or gauge symmetries, as Axel said, that are not broken, not those, and the fact that they are not broken is just because, well, sure, because they just translate the fact of the physical fact of relationality.
Yeah.
So yeah, at least that's how that's my provisional understanding of things.
No, I think that's right. I agree with that. It's also how I view things.
Okay, perfect. Thanks so much. So if there is no further question, then thanks again, Jordan, so much for the talk. This was amazing. Also, thanks so much for the discussion. This was really, really fruitful, really, really interesting. Yeah, it was great to have all of you. And we're looking forward to our next meeting whenever this will happen, but we will be in touch and let you know.
Yeah.
Okay. Bye-bye.
Thanks, Jordan.
Yeah.
Bye.
Thanks for being here.